let's look at this question, examining the light released by a firefly. So we're told that wavelengths of light emitted by a firefly span the visible spectrum, but have a maximum intensity near 550 nanometers. Now, a typical flash of light from a firefly is very brief. If you've ever seen them, you'll suspect this. So let's say, for this question, the amount of time in one flash is 100 milliseconds, and it has a power output of 1.2 milliwatts. The question is, how many photons does a firefly emit in one flash if we assume all the light is emitted at that peak intensity wavelength? Okay, so what do we know? We have a wavelength of light that we're going to work with, which is 550 nanometers. We have an amount of time for the flash of 100 milliseconds. We also know the overall power. So the power of that burst is 1.2 milliwatts. So the question is, find n of photons. So how are we going to do that? Well, we're going to start by recognizing that we've been told pretty much right there how many photons have been emitted. We've been given the power. And so the power is related to the energy in time. And the energy is going to be divided up amongst n photons of an energy corresponding to this wavelength. So that's how we're going to work this out. We're going to look at the entire burst and then divide that energy between n photons corresponding to that wavelength of light. So power is equal to energy over time. In this case, that energy is the whole burst. So I'm just going to make a little note of that. So that's the energy of the entire flash of light. Okay. And so then the power is going to be, well, let's break down that total energy to be n times the energy of an individual photon. I erased a little bit more than I wanted there. There we go. Okay. And divided by time. Now let's figure out how much energy is in each individual photon, and then we will be well on our way to having ourselves the energy and thus the number. I'm going to leave it there for now. Let's come over here to the side and look at what is the energy per photon. That's going to be HF of the photon. Okay. But how do we relate the frequency to the wavelength, which is what we have? Well, if you remember from waves, the frequency of a wave is related to the velocity over the wavelength. In this case, the frequency of a photon is going to be c, because photons are traveling at the speed of light, divided by the wavelength. Okay, so we can say the energy of the photon is equal to h c divided by the wavelength. Okay, Now let's bring this into our other equation here. So now we've got n. We got to isolate for n. So we're going to have power times time divided by the energy of the photon and so that's going to be P, T, and then we're going to have HC over lambda. All right, so now we're going to just simplify and substitute in. So the number of photons is going to be lambda P T divided by HC. So our lambda value was 550 nanometers. Just going to make some room here. Great, okay. So 550 nanometers times the power, which is 1.2, and that was milliwatts, so times 10 to the negative 3 watts. Time was 100 milliseconds, so 100 times 10 to the negative 3 seconds, and then H times C. And in SI units, it's going to be 1.989 times 10 to the negative 25. That's joule meters. Okay, that will give us 3.3 times 10 to the 14 photons. Does that sound reasonable? Well, that's a lot of photons, but each individual photon doesn't carry that much energy. So this is a sensible result. And that's all.